All right, good morning. Well, thank you, Josh and John, for all of the bad news in the past couple presentations. But you can't have good news without bad news. So luckily, John was nice to give me the good news presentation. So my name is Michael Mansfield. I'm with the Army Corps of Engineers, Kansas City District, and I'm the technical lead for this project. Want to recognize Laura Totten right here with the Corps of Engineers. She's the project manager from the Corps, and then Josh is the project manager from the state side. So this project has been funded both by Army Corps of Engineers and the Kansas Water Office, so it's been a joint project. Okay. All right, a little bit of outline. I guess we are going to have a little bit more bad news, and then I'll go straight to the fun stuff about water injection dredging, talk about some of the theory, what we've done over the past couple months, and then what our way is moving forward. So you've already seen this slide, no need to rehash it. The one thing that I will add is that we talk about trapping efficiency with regards to like how much sediment is coming in versus how much sediment is leaving. And at Tuttle, that's about 98%. So you think about 98% of the sediment that is coming into Tuttle stays in Tuttle. So that's why these projections are so bad. There's a very large sediment load coming in, and then 98% of that comes in, and then 2% or a little bit under maybe is what's leaving. So very turbid water coming in, artificially clear water coming out. And then just to reiterate on those low-lying gates, so this is a picture from when Tuttle was under construction, and you can kind of see these wing walls. This is on the upstream side. So these gates are at the bottom, which is why water injection dredging is even viable at Tuttle Creek Lake. And so yeah, it's a nice little figure before, during construction. So here's water injection dredge. This was given to us by Kumar. So Custom Dredge Works is located in Topeka, so it's a local local company, built and designed the water injection dredge. And yeah, here's the schematic. Kumar, wave your hand. There you are. Great. Yep. So yeah, thanks for this. This is great. And I'll talk a little bit more about it. But the general idea with water injection dredging is that you're injecting large volumes of water at low pressure into the sediment bed to create a density current. And so I'll explain what that is in a minute, but basically just want to differentiate this from agitation dredging. So agitation dredging would be stirring up all the sediment and trying to get it up really high in the water column. And you might see this in like a river where you've got fast moving water and you're just trying to mobilize a shoal, for example, a navigation channel, and you're just trying to stir it up into the water column. In a reservoir, you don't really have a current, and so you're really relying on the density difference and the pressure gradient of that density current in order to move the sediment to where you want it to go. So water injection dredging is not a new technology. It's been around for several decades now, and it's primarily used in ports and harbors, primarily in Europe, but also in South America and in Africa, and a little bit in the United States. But it's never been done on a reservoir before. And so we are, this Tuttle Creek Lake demonstration is the first time that it's been done on a reservoir, so we're learning as we go. A little bit more about a density current. So in salt water, the density is around 1025 kilograms per meter cubed. Whereas fresh water is around 1,000. And then a density current is denser than that. So when it's performed in salt water, you're generally looking at density currents that are around the 1,100, 1050 to 1,200 kilograms per meter cubed. And because that's denser than the surrounding water, the density current, like Josh was showing in that video from the Engineering Research and Development Center, is going to move of its own volition. And so the driving forces are the density difference, and the resisting forces are the bed friction and the settling of the density current. And you can see here this density current is moving because in a port or harbor, you're going to have like a steep, you might have like a steep bed slope, and so it's going to give you a little bit of a benefit there. In Tuttle Creek Lake, it's a very shallow bed slope. So there's a couple of differences between what we're doing and what's been historically done. And so again, we're learning as we go. And also in a port or harbor, you're generally just trying to make it soft enough so ships can sail through, whereas we're trying to replace the water storage. So several differences depending on what we're doing. So yeah, and then here's another nice little figure from a thesis out of TU Delft, and that just kind of shows the stages that a density current will go through. As the water injection dredge is moving to your left, it's going to create a really fast-moving density current, what we call supercritical flow. So it's fast and shallow. And then if the bed slope is pretty shallow, like it is at Tuttle, we expect it to go through a hydraulic jump pretty quickly. And then that's when the density current is really going to start moving of its own volition, just based off of the density differences. So here's some production rates based off of European water injection dredging projects. I just want to comment a little bit about these production rates just vary wildly. Some of the biggest factors for how much sediment you're going to be producing with water injection dredging are obviously your sediment type, your bed characteristics, and then even the crew. So I was having a conversation with the professor out at TU Delft a few months ago, and he said that at the same site with the same wood vessel, they actually see pretty drastic differences in the production rate of that water injection dredge, depending on when they have one crew change to the other. So there's a large learning curve, especially with this water injection dredge. It's not as maybe cookie cutter as sucking it up and putting your pipe where you want it to go and then just moving it around. So there's definitely science. There's a lot of art to these as well. So those are European ones. It's also been done somewhat in USACE. A lot of these are in ports and harbors and some in rivers. Generally, you'll see that the lowest production rates occur when you've got coarse material. So like anything that's like sand, you're probably going to have a pretty low production rate because sand has a pretty high settling rate. And like I said, one of the resisting forces that you're going to have with a density current is settling. And so at Tuttle Creek Lake, we've got generally 60% clays, 40% silt, and most of that, and maybe a smaller fraction of sand. And so very low settling rates, so that helps us in our planning purposes that the density current isn't just going to be stirred up and settle really quickly. It'll give it time to be able to make its way out. Oh, and then just one more comment on the, I can go back, right? Yeah, I can, okay. One more note on the production rates. So you'll notice that a lot of these, they basically have the cost, now the cubic yard, and the duration. Well, if you're going to be doing this operationally in a reservoir, for example, just note that in a port or harbor, you've got kind of like a finite area where the ships are going to be operating. In a reservoir, you're really interested in the whole storage capacity because your whole reservoir is going to be contributing to your available water storage. And so, you might have a very high production rate when you're operating close to the dam, and you might have a very low production rate as you're moving farther away from the dam. So generally, when we're talking about, production, how much, is the water injection dredge going to be producing, we do expect that it will vary throughout the year and throughout where the dredge is operating. So just note that we're probably going to be looking at this on a longer time scale. We're not just going to say each day, here's how much we produce, like you might in one of these projects. So here are some of the project goals. So this is a research project. We haven't done water injection dredging in a reservoir before ever, and so our primary mission with this is to assess whether or not this technology could be used to effectively remove sediment at a cost-effective rate. And we want to determine, how much does it cost, how much can we move, and then what are the downstream impacts. So if we can answer these questions, then we'll consider this demonstration fully successful. We've got a lot of data that's being collected in addition to that. And to answer these questions, we've got 3 dredging periods. So we did fall 2025, and then we did spring 2026, and then soon, in the next couple of weeks, we'll be doing the final dredging demonstration during the summer of 2026. So each of these dredging periods consists of 200 hours, or roughly 10 days, of active dredging. And we're measuring before and after surveys to determine how much sediment was removed. We're looking at downstream impacts, and then collecting a whole slew of other data as well. So just to reiterate, the goal is not necessarily to dredge to a certain depth or to remove a certain cubic yard. Once we can answer these questions, then we'll be able to position ourselves for future implementation if it's warranted. And then, like all good engineers and scientists, we're really good at coming up with other questions we can ask. And so a lot of these other questions revolve around the density current transport. So how far does density current travel? What sort of density current are we creating? What are some of the ideal operation parameters of the dredge? And then we also want to know inlet chemistry, and then downstream, we're also interested in fish population response and downstream deposition. Here are some of our collaborators, lots of federal, state, and academic partners that are helping us answer some of these questions, and many of them are in this room today. To answer, in particular, just want to comment on the dredging period. So during the fall, this was the first time that we've performed it ever, and so our main goal with the fall demonstration was to determine what are our optimum dredge parameters. So we varied things like speed, direction, nozzle configuration, standoff distance from the bed, and then in the spring, we were really trying to see, okay, what did we learn from the fall demonstration, and then how much can we produce? We want to be able to operate optimally. And then during the summer, we knew that we'd have some temperature and pH restraints. So we're trying to adaptively manage to make sure that all of our downstream impacts are mitigated and we don't have any, and that we're able to operate, what do we need to do in the future to be able to operate in the summer during these warmer months when pH is high, when temperature is high, in order to still have acceptable impacts downstream. So you're probably sick of this graph. We didn't coordinate our slides very well, apparently. But yeah, this is what's coming in. So very wide variety. And yeah, at 2,000 CFS, which is generally the flow that we operate at during the fall demonstration, yeah, you can see very wide, up to around 5,000 milligrams per liter. I really like that jelly bean slide. I need to steal that from you guys. But yeah, and then during the spring demonstration, we actually varied the flows a little bit because we wanted to see, what actually happens to the density current and downstream impacts when we're at 1,000 or 1,500 CFS, or what if we increase it to 3,000 CFS? So more on that in a minute. We have a lot of monitoring. So like with any novel project, we want to make sure that we are monitoring it appropriately and that we're able to characterize any sort of impacts we might see. And so we've got 6 main monitoring locations. There's one downstream on the Big Blue River, about 3 miles downstream of the dam that the USGS operates. And then we've got a control site upstream of the confluence on the Kansas River. And then we've got an impact site downstream on the Kansas River at Wamego. And then we've got several other sites downstream in which we're collecting bed gradations, cross sections, invertebrates, water quality, and so all of these are being extensively monitored. Can I do this? Can you click the video? Well, here's our dredge. So this was flown by Tony Lazelle, who's in the room. And so you can see that our dredge is around 40 feet wide. It's about 120 feet long, and its pumps have the capacity to pump around 32 to 40,000 gallons per minute. And so, again, lots of volume of water. But when you get to the actual nozzle, it's only around 15 to 20 psi. So relatively low pressure for a large water jet like this. And it operates around half a knot to 2 knots, so operating fairly slowly. Yeah, I think those are all the main things. Yeah, I guess there's 78 nozzles, so it's pretty. The nozzles are spread out pretty evenly across the jet bar. And we, again, like I said, during the fall demonstration, we changed the. Oh, that's not part of the video. Yeah, so we changed some of that in order to determine what the optimal dredge parameters would be. Okay, here's the dredge plan. Like I said, so during the fall on the eastern floodplain, we varied a lot of those parameters, and you can see these test lines that are spread out from each other. So we wanted to test these parameters and not have impacts on the other lines, and so we dredged these lines on the eastern side during the day, so we could monitor it. And then on the west side, we had those lines on the west side closer to the dam, and those ones we dredged at night that were primarily aimed at production. Here's the spring 2026 dredge plan, and so we operated, a little bit differently. We were, trying to optimize production, and we started at the northern end, and then we worked our way down, and so, yeah, and then we dredged pilot channels about every day with those ones. Okay, so this was about 5-10 minutes after the beginning of WID during the September dredging. Josh, John, and I, and a few others were at the downstream channel, and this is when we did our victory lap, because we saw the sediment within a few minutes starting to come out of the gate, and so that was really exciting for all of us to see. Here's a nice video that Ariel Kramer with the USGS collected for us. Okay, so you can see here, started off clear water, and then just within a few minutes, the turbid water started flowing. And then I'll just comment that none of our downstream limits were exceeded during either our fall or our spring dredging period. And so even though you saw that turbid water, that's still not as turbid as what was coming into the reservoir. We did operate 24/7 during each of these. And so yeah, this one was collected during the fall as they were getting close to the dam for one of their pilot channel sweeps. Here's some preliminary data that the Engineering Research and Development Center collected. So this was courtesy of Dr. Drill Smith, and so they had an AECP downstream within the reservoir, but downstream of the water injection dredge. And you can see the spikes. So this was their confirmation that the density current was being transported. So you can see the backscatter correlation. They're analyzing it to determine how fast was the density current, where its dimensions and such. So all of this data is being analyzed now. This was the fall 2025 turbidity. So you can see that these large spikes generally correlated with when the dredge was getting close to the dam. So we dredged in the eastern floodplain or on the western floodplain for a few hours, and then we did these pilot channel sweeps, and so we moved back down towards the dam. And that's generally what correlated with those large spikes. And then we kept flows elevated for 2 days before and 2 days after dredging. And so the turbidity slowly decreased back to pre-WID conditions over the following month or so. And you can see here as well during the spring 2026 demonstration. So it started off low, generally correlated with lower flows, and then we increased production throughout the dredging period. And then similarly, we saw the turbidity slowly creep back down towards normal conditions in the month afterwards. So this is a graph that I am particularly proud of because it took me several weeks to develop, but and I know it's pretty messy, so I'll probably clean it up for the final report. But I just wanted to show, so you can see the concentration, which is the black line. So the concentration is going up and down. And during the spring, we had a lot of issues with weather. Apparently it's windy in Kansas during the spring. And so, that kind of gave us good data, though, in that we could see when the dredge was operating, we saw the concentration signal starting to respond downstream at the USGS gauge, and then once wind shut us off, then we saw the concentration drop pretty quickly. So we saw that response within a few hours or so. You can see here that even, we generally saw the highest peaks during those pilot channel sweeps, but then we also saw, even while we were dredging the eastern floodplain, so that's what these green lines represent, when the dredge was operating on the eastern floodplain, we saw a response at the downstream gauge. And so we also varied the flow, and we saw that as we increase flows, we increase our concentration, and we're analyzing this right now, and we're going to collect some additional data during the summer to really determine what the cause was of this. It could have just been deposited sediment downstream that at those lower flows, it was picked up at the higher flows, and then, or it could have an actual in-lake effect. So we're analyzing that now. And then after the demonstration was concluded, we increased flows to 4,000 CFS to flush anything else that would have remained. So you saw a small little spike towards the end, but then after the dredging concluded, the concentration drops pretty quickly, even with the increased flows. So here are our next steps. So within the next few weeks, we'll be completing the third and final demonstration. And then after that, we'll be analyzing all of the data. We'll get some estimates for how much volume was removed, and then we'll look at cost as well. And then we'll look at the sediment characteristics that were passed downstream to get some water quality information. So that'll all be published in a USACE technical report. And then we'll also have some intermittent reports and journal articles that'll be coming out answering some of those secondary questions in the near future. So with that, I'll open it up for any questions. Yeah, so I guess when you talk about base flow, it varies wildly, obviously. So we did store up into the flood pool, so we stored up several feet into the flood pool above the multipurpose in order to sustain that 2,000 CFS release. So yeah, generally low flows are probably around 500 CFS. We were operating around 2,000 CFS. And so obviously sometimes we were holding water, sometimes we were passing inflows. Yeah. All right, I'm gonna do my best to answer, but I'm not a fish biologist, so I might point you to Keith Guido afterwards. My understanding is that the fish have a slow response time, whereas invertebrates have a fast response time. And so generally, we wanted to see what the quick response was, and then that would inform the fish response. Is Keith here? Does Keith want to? Oh, great. Okay, great. Sure. So for those that couldn't hear, so the question was, what characteristics of the density current do you need in order to make the density current leave the dam, right? So like velocity, concentration, slope. Is that right? Is that your question? Yeah. Okay. Yeah. So yeah, we don't have estimates on that. That'll probably be answered from an academic perspective. So we'll be setting up numerical models to be able to understand how, what the critical concentration, slope, height of that density current is. So yeah, we probably won't be answering that with this demonstration. We may be able to get, kind of scratch that itch a little bit with some of the data that the Research and Development Center was able to collect with ADCP and maybe some of the list data we'll be collecting this time, but we probably won't have a great answer for that until we set up a solid CFD model. Yeah. Yeah, there are a few proposals in right now. So John's going to be looking at that with one of his students over the next few years. And then, yeah, the Engineering Research and Development Center is exploring opportunities. Nothing definitive on that yet. But yeah, I think that there's certainly a need both for understanding the physics of the density current and then also the software side of being able to implement it into whether it's a quasi 2D model or a full 3D model to be able to analyze all of the sediment characteristics, the bed slope, the changes, of the dredge operability, which will play a big role. So yeah, I think that there's several avenues that need to be explored, and I think that they're being explored adequately right now. Yeah. Anything else? Yeah, not yet. I think we'll be able to answer that with some of the data by the end. It certainly seems like there was a strong response at the gauge depending on the flow. So I think we will be able to get there, but I don't think we have the answer yet. So stay tuned. Yeah, that's a great question. And I guess short answer is we don't know yet, but I think we'll get there. I think we'll have to look at the wind speeds and traditional typical wind speeds that made us not able to operate. So we'll be able to answer that some from the spring data. We'll need to look at what flows are able to be sustained in order to pass the sediment. So yeah, I think we'll get there. With this demonstration, hopefully. I think some of it may be a little bit more back of the envelope than we'd like, maybe. But yeah, we'll see. Yeah, so the system that Michael's and Custom Dredge Works uses basically takes the multi-beam survey that's collected and then it adjusts the boom automatically, so that way it won't hit the bed. So what the specifics are, I probably can't answer well, but that's how they're doing it. Well, thank you all very much.